So now we can get into the first sort of physics topic. And that is particle kinematics along a line. Okay, well, there's 3 bits of information in this long title. One, it deals with particles. Second, it's kinematics. And third, it's along a line. So what do these things mean? So particle means that we're treating objects as if they have no length dimensions. You know, it's like the size of a point, infinitesimally small. They do have mass, though. That won't come up for a little while, but and the object's location is the object's center of mass. When you think of particle physics, what that generally means is that you're dealing with things that are smaller than an atom, parts of an atom. Okay, that's not what I'm talking about here. It turns out that, you know, like a lot of the important physics right now is going on with subatomic particles. And things that are really small, it's pretty reasonable to treat them as if they have no length dimension. So that's why that's called particle physics. But you can treat anything like a particle if you just throw away the information about its length dimensions. Like, for example, if you're doing calculations involving planetary motion, people treat those as particles almost always. Really, the only thing that you need to treat something as a particle is you need to not be interested in the orientation of the object. Okay, so if you want to track Jupiter's path as it goes around the sun, and you don't care what direction the spot on it is pointed, then you treat Jupiter as a particle because it's a little simpler to do. Okay, but you can't calculate an object's orientation this way. So you can track where it goes, but you can't track which way it's facing. There are a lot of times when you need to know an object's orientation where that's important information, and in those cases, you can't do this. But we're going to start out by just tracking the location of the center of mass of objects as the object moves around. And if it rotates or whatever, we're just uninterested in that information. Okay. The second bit of information in this title is kinematics. Kinematics, that word is used as opposed to kinetics, which is the next thing we'll study, and it seems ridiculous, unnecessarily confusing that these two topics we're going to deal with have almost identical names, but I don't know. People already named them. We don't get to really rename them. So kinematics is the one we're starting with. It's the simpler of the two. And kinematics deals with describing an object's motion without the causes of the motion. And the causes of the motion we'll think of as force and mass. Another way you can think of this is it's just relationships between time, position, velocity, and acceleration. So that's all we'll be doing in this first topic, is dealing with those four things and a couple of closely related things. And then along the line is pretty self-explanatory. So eventually we'll be dealing with things in 2 dimensions. Most of the class will be dealing with things moving in 2 dimensions in a plane, like moving along the board. But we're going to start out by just thinking of things that can either go forward or backwards along a line. Let's think of this as at any instant, there's only 2 choices about which way to go. So like if this is the line and this is the particle moving along the line, it can go this way or it can go this way. We're going to see that that's really easy to deal with mathematically, because if there's only 2 choices of where to go, you can call one of those positive and one of them negative, and then the sign of the numbers that you're dealing with represents which direction it's going. Okay. Later on, when we go into a plane, you have an object here. It can go infinitely many directions, right? And we obviously don't have infinitely many signs. So positive and negative aren't going to be enough to tell us direction. And so we're going to have to come up with a new thing, which is vectors. Okay. But we're going to start out with these concepts just in the simplest mathematical way we can, just representing the direction by the sign. Yep. A curvy line, this applies in some ways to curvy lines too. If you throw out the stuff that's going on, if you throw out the stuff that's going on perpendicular to the curve that it's traveling along, this gives information about the stuff that's parallel to it. We haven't talked about enough really to make sense out of that, but you can think of it as like, yes, this stuff works, but you have to be careful. You know, you can use it, but you have to be careful. Any other questions right now? All right, well, obviously, since we're dealing with relationships between time, position, velocity, and acceleration, we have to define these things. So I'm going to start out by defining position. Okay, so say that you have an object at a given location. Okay, so like, you seen my chicken? Yeah, it's over by the store. You know, that's a location, a physical place in the physical world. What does it take to describe that location numerically? You know, what does it take to assign a position number, a position value to this object's location? A numeric value to the location. Well, it takes two things. First, you have to choose some reference location. Um, that's our 0 position. That's like where we're going to start measuring from. And then second, since we're dealing with motion only along a line, and there's only 2 possible ways you can go, we need to choose a direction that we're going to call positive. So we have to choose a positive direction. Okay, so let's see. Starting to realize why I didn't have this as a bicycle in my notes. Okay, getting there. So this bicycle is moving along this line. Okay, and the center of mass is, say here, the center of mass actually doesn't have to fall on the physical body. That's sort of an odd factoid. You know, good high jumpers, you know, high jump, they use the back flop thing. Can you picture like they run up, turn around, and go over backwards? The reason they do that is because that way of doing it is very efficient at getting points of your body higher than your center of mass at any instant. And so a very good high jumper can actually get their entire body over a bar, and never at a single instant is their center of mass above the bar. Their center of mass goes straight under the bar, and one by one, each point gets over the bar. That's pretty cool. Because your center of mass height is just determined by how well you can jump. But if you can get your body higher than that, then you can get over a higher bar, you know. Okay, so what's the location of this? You know, this is the line of travel. So we can see physically the location of this bike rider, but what's it going to take for us to put a number on that? Okay. So the way this works is, first, somewhere along this line, we're going to choose our 0 position. Okay, so That's arbitrary. Although once you choose it, you have to use it consistently for the whole rest of your calculation. Okay. Uh, and then we have to choose a positive direction. There's only two choices of direction. It's along that line of travel. And we could choose either one. Let's say that we choose the positive direction to be this way. Well, now that we've chosen that, we can just measure the distance from the zero position, that reference, to where the person is. Let's say that that's, what does that look like? 2.5 meters. So then numerically, what's the position? The position is a distance of 2.5 meters. And then when you start in the zero, are we going in the positive direction or the negative direction to get to the bike? Negative, so the answer is negative 2.5 meters. That's the position. Any questions about that? Position units are always length, and so if you're in SI units, position is in meters. Okay, so I want you to notice a couple things about this. So once you choose a positive direction, the sign of a number is equivalent to an arrow in space. So it's either that way along the line or that way along the line. And so you can always represent the direction in two ways. You can represent it by pointing an arrow in the direction of the value, or you can do it with the sign of the number. Okay. I mean, we're always going to do it with the sign of the number, but I want you to get used to this idea that the sign of that number represents an arrow. They're equivalent to each other. So like you could think of this as the position is negative 2.5 meters, or you could think of it as the position is 2.5 meters that way. Okay. If you also choose an instant that corresponds to time equals 0, then you can plot a position versus time graph. And plotting a position versus time graph is equivalent to representing the position as a function of time. So think of choosing a time equals 0 as like when you click your stopwatch on if you're trying to time something. Like when you time a 100-yard dash or something, there's a specific instant that you start your stopwatch running, and that's when they start running. You know, if someone was like, time me for the 100-yard dash, and they run, and you're like, what? And you're like, 6.5 hours. And they're like, what? And you're like, yeah, I started it sometime earlier this morning. They wouldn't be very happy, you know. Like when you choose your time equals 0 instant, it, you know, affects the answer you get for what time an event happens. Quick. So let's say that there's a swimmer standing on the shore wearing swim trunks, and there's a raft out here, and he wants to swim out to the raft, and let's say the distance between them is 50 meters. And let's say it takes, how long does it take to swim 50 meters? 2 minutes. Let's say it takes 120 seconds to swim to the raft. Let's say that we want to plot a position versus time graph where the position equals 0 is on the shore, and the positive direction, well, let's choose sort of an unusual one for this. I mean, you can choose anything you want as long as you're consistent. Let's choose the positive direction away from the raft, so opposite the direction to the raft. Okay, so either way, the motion, so if this is the line that the swimmer's moving along, and he starts out here at the shore, and he ends up here at the raft. Oh, and I didn't give, let's say also the 0 time is when he starts swimming. If a problem doesn't say anything about that, you can just always assume that the 0 time is when the motion starts. Okay, well, the swimmer is at the shore at 0 seconds. And what's the position of the swimmer at the shore? 0. And we chose this as our 0 position, and we chose this as our positive direction. When the swimmer gets to the raft, the time is 120 seconds. And what's the position? Yep, the distance is 50, and then it's in the negative direction, so this is negative 50 meters. And so a position versus time graph We start at 0, 0. We end at, not there, but we end at, damn it. So that's 120 seconds. We end at a position of negative 50. And so the graph looks something like that. Okay, and what that graph looks like is dependent on your choices of those three things. The time equals 0, the position equals 0, and the positive direction. Okay. I said, so we're always going to, this is the last quick thing. We're always going to draw our graphs with position on the vertical axis and time on the horizontal axis. We're always going to represent position as a function of time, not the other way around, not time as a function of position. You could think of that as just sort of a convention. That's what people do. But can you think of any reason why we would do it this way and not the other way? Yeah. The position you could end up, he could swim back and end up back at position 0. He could end up at a certain position a million times, but a time only happens once. And so that's the definition of a function. You have to have just a single value for the function once you choose a value of that independent variable. So it doesn't work the other way. It wouldn't be a function. So without a function, you can't take derivatives. You can't. There's a lot of stuff you can't do. Once you have the position defined, you can define displacement. It's related to position. If you choose two instants, T1 and T2, then the displacement between those two instants and I'll call it lowercase d, is the position at the later time minus the position at the earlier time. A couple of things to notice about the displacement. Displacement has two pieces of information in it. The first one is the absolute value of the displacement, the magnitude of it. Is the distance between the two locations. And the sign is the net direction the object is moved over that time interval. Okay, so again, this sign you can think of as you can always think of the sign, which is, the sign is a mathematical thing. as equivalent to an arrow in the space where the motion occurs. So the sign is like in math world, the space where the motion occurs is in, you know, the real world. Okay, so let's say that you have an object moving around on the floor. And let's say we're calling this the positive direction. Okay. And let's say that the motion of this object, and you know, we would have also had to choose a 0 position somewhere. Let's say that we'll call this the 0 position. And the position of the object over time is given by the function p of t is equal to 2t cubed minus 20. Let's say this is in meters. Okay, so first, what's the displacement from time equals 0 to time equals 20? Oh no, that would be big. Time equals 1 second. What's the distance between the locations at these two instants? And third, what direction is the arrow in the direction of the object's net motion? Okay, so to figure out the displacement, we have to figure out the position at these two instants. So the position at time equals 0 is 0 cubed times 2 minus 20, so negative 20. The position at time 1 second is 2 times 1 cubed minus 20, so negative 18. And since this is all given in meters, the units are meters for each of these. And so the displacement is just the position at the later time minus the position at the earlier time. That's negative 18 minus negative 20. So that's positive 2 meters. Okay, so What's the distance between those two locations? The distance is the absolute value. So again, that's 2 meters. And the net direction, well, it's a positive sign, so it's moving in the positive direction. So now back in the real world, the world where this object lives, the positive direction is to the right, so the arrow is to